In this video, we are going to get acquainted with rational functions by looking at graphs and equations of rational functions. We're going to learn various features that are new to us in regards to how rational functions are shaped, and we're going to see lots of examples of how to work with them just in general. So to start, we're going to start with the most familiar rational function, the parent function f of x equals 1 over x. If you remember that graph, it's in two pieces. And we filled out a table previously, and the most important part of this rational function is that at 0, we do not have a value because you're dividing by any x value you put in. You do not have a value. So let's start our table right here in the middle. When x is 0, y does not exist. That's what DNE stands for. Then if we spread out from there, let's just start with 1. Positive 1 going in, 1 divided by 1, that's just 1. And then 1 divided by 2, moving over to x is 2, the bottom of our table. We get a small number, 1/2. So what I like to say is big numbers make small numbers in rationals, which therefore means that small numbers make big numbers. So if we plug in 1/2, our rational would look like 1 over 1/2, which really is just equal to 2, because you flip the bottom fraction over, making it into a 2. So small numbers make big numbers make small numbers, and it works the same way for negatives. They're all just negative. So -1 makes -1, -2 makes -1/2, and then -1/2 being plugged in makes a -2. So if we can plot those points into our graph, we have 1, 1, we have 2, 1/2, so it gets closer to the x-axis, and then we have 1/2, 2, so it goes up towards the y-axis at the same time. On the negative side, we have -1, -1, -2, -1/2, so we're getting closer to the x-axis again, and then -1/2, -2. So those three dots right there are separate from the other three dots in the first quadrant. So we'll connect our line by sliding down the y-axis, curving, and then sliding along the x-axis. Draw an arrow at the end, one points up, one points to the right, and then we'll do the same thing in quadrant 3, slide along the x-axis, curve, and then slide along the y-axis. One thing that's important is to not actually cross the x or y-axis in this point. The rational functions will not touch certain points, so be careful with that. So if we fill out our domain, if we look from left to right, it looks like we have pretty much every number. So when we have every number in our domain, we put all real numbers. But if you look back at our table, and you can see it on the graph, we skipped over 0. So we have all real numbers, except we skipped over one number. So the way we write that is put a semicolon, and then we just say x does not equal 0. So we have every number, all real numbers, except x does not equal 0. If we look at the range, the y's, the same thing happens. From bottom to top, it looks like we have everything. There's an arrow pointing all the way down and an arrow pointing all the way up. But once again, it looks like we skip over at 0. So we're going to write the same exact thing for our range. All real numbers, but y does not equal 0. Keep in mind, range is y, domain is x. So this is a unique thing that we've seen before, is that we can just skip over one number in our domain and range. So to define our domain for rational functions, we have the values that make a function defined over the set of real numbers. So we can't plug in 0 because that's not a defined function. You can't divide by 0. So it's not a part of our domain. The second part, the domain of a rational function eliminates values that cause division by 0. So like I just said, anything that you are going to plug in that would cause division by 0 is not allowed to be a part of your domain. So in order to find that, in certain cases, it's not as easy as just saying, oh, well, we can't include 0. In order to do that, we set the denominator equal to 0. The bottom is where the issues occur. So that's what we set equal to 0. So let's look at these examples here. They're just asking us to find the domain for 1, 2, 3, and 4. So For number 1, we have f of x equals x plus 2 over x minus 4. All we want is the domain. So all I need to do is take x minus 4 and set it equal to 0. This is going to tell me what number I'm not allowed to plug into the bottom. Now it's just an equation. Add 4 to both sides and you get x equals 4. So 4 is my issue. If you just want to test that real quick, plug in 4. 4 plus 2 over 4 minus 4. The top is 6, but the bottom 0, so that's a no-go right there. So we do not want that case. So let's state our domain. I'll just write a D for domain. It is all real numbers, except we don't have 4. So all real numbers, x is not equal to 4. And that's it to find that domain right there. Looking over at number 2, we have 2 minus x over x. And we're just going to use the domain once again. This one actually looks somewhat similar to our parent function, that the x is the only thing in the bottom. So we take x, set it equal to 0, and we don't even have to solve that equation. We're not allowed to plug 0 into that equation. So our domain is all real numbers, except x does not equal 0. It's pretty convenient to say all real numbers, except skip one number. It'd be really difficult to list out all of those numbers. Actually, it's impossible. For number 3, we don't actually just start by taking the bottom and setting it equal to 0. One thing you have to keep in mind about rationals is factoring first. So x plus 3 can't factor on top, but the bottom is x squared minus 4. That's a difference of squares. So the square root of x squared is x, and the square root of 4 is 2, so it's x minus 2 times x plus 2. So the rule says set the denominator equal to 0. But if we have multiple factors, we just take each factor and set those factors equal to 0. So x minus 2 is equal to 0, and x plus 2 is equal to 0. Now we're going to have two numbers we don't include in our domain. One of them is positive 2, and the other one is negative 2. So to state our domain, once again, we have all the real numbers, but we're going to skip over two numbers. To say that, all we have to do is list them. Negative 2, comma, 2. I like to put them in low to high order. It does not matter, though. So all real numbers, x is not equal to negative 2, comma, 2. And the last one of these examples, we have f of x equals 5 over x squared plus 2x minus 8. We are going to have to factor again. So f of x equals 5 over, we have an x puzzle that we need to solve here. It's going to start with x. We need to multiply to negative 8 and add to positive 2. Well, that's 4 and negative 2. So plus 4 and minus 2 go into the back of my factors. So now I take both of those factors and set them equal to 0. X plus 4 equals 0. And x minus 2 equals 0. Solving both of those, I'm just going to go straight to the domain. That'll tell me that my domain is all real numbers, except x does not equal negative 4 and positive 2. Solve those, set them equal to 0, or get them equal, get x by itself, that's what I mean, and you get negative 4 and positive 2. So now we've seen domain for rational functions, and you can see a new word. This is what some math teachers will say is a mathematician's favorite word, is asymptote. We are going to see asymptotes on graphs in that curves will look like they're getting really close to something but not actually touching it. That's my idea of an asymptote. What is the graph, the curve, getting really close to but not actually touching? So our definition of asymptote is a straight line approached by a curve, and I'm saying curve in the same place as the word function. So rational functions are curves. So a straight line approached by a curve as one variable, so either x or y, approaches infinity. So that means asymptotes occur at the very top of your graph, the very bottom of your graph, or the very right side of your graph, or the very left side of your graph. Infinities are always on the ends of your graph there. So these asymptotes actually were on the graph that we had up at the top, so we're going to go back up to the top and look here. You can see we flattened out along the x-axis and didn't want to touch the x-axis. Well, that's because there is, in fact, an asymptote along the x-axis. This asymptote moves horizontally, so we call it a horizontal asymptote. I will label it as HA for that. And then we also didn't touch the y-axis. So we have another asymptote that goes down the y-axis. This one is a vertical line, so we're going to call this a vertical asymptote. Horizontal and vertical asymptotes don't show up when you graph on Desmos or on a calculator, but we have to know that they're there. We draw them onto our graph as dotted lines so that they don't look like the actual part of the graph. You can label them as vertical asymptote, horizontal asymptote, but they are lines, straight lines that graphs do not like to actually touch. So let's get into the specifics of what a vertical asymptote is and what a horizontal asymptote is. So for a vertical asymptote, they occur when the denominator equals 0. So this is linked to our domain. Vertical asymptotes are pretty much the same thing as our domain restrictions. There's one special case that we'll get to on the next page. The graph will never cross a vertical asymptote because these values make the function undefined, meaning we tried to divide by 0, but we're not allowed to do that, so we can't include that value. Sometimes vertical asymptotes, or not sometimes, always vertical asymptotes are called non-removable discontinuities. Non-removable. Awesome. So you saw that on the top there. We had that yellow dotted line. That was our vertical asymptote of our parent function. We'll see some on the next page. The other version of asymptote that we are going to see is a horizontal asymptote. So horizontal asymptotes are found by evaluating the degree of the numerator and the degree of the denominator. So what that means is in order for you to determine where the horizontal asymptote is based off of an equation, you would do the following steps. What a horizontal asymptote is that straight line that moves straight across that your graph flattens out across. So given an equation, I'll even put that here, given an equation. If you have a graph, just look for where it flattens out on the ends. That'll be where your horizontal asymptote is. But given an equation, you check the degrees to determine where your horizontal asymptote will be. So we're going to check the degree of the bottom and the top and compare them. So the first case would be if the degree of the denominator, the bottom, is bigger than the degree of the top. So my nickname for this is big bottom. I know it's silly, but when your rational function has a big bottom, the horizontal asymptote is y equals 0. That's always the case. It's always y equals 0 if the denominator's degree is bigger. The next case is if the degree of the denominator equals the degree of the numerator. So the bottom matches the top. My nickname for this is just same. So sometimes I'll make a note and say, oh, the degrees are the same. In that case, if the degree of the denominator is equal to the degree of the numerator, the horizontal asymptote is found by the ratio of leading coefficients. So once we check those degrees, when they match, we would take the ratio of the leading coefficients to create our y equals. Our y equals is always how we're going to start a horizontal asymptote, and then it could be some type of number. It won't be 0. 0 only happens when the bottom is bigger, but then it'll be some type of number for our horizontal asymptote when the degrees match. So let's just look at an example here. Number 1 from this domain example, we have f of x equals x plus 2 over x minus 4. So when we're checking degrees, we're going to look just at the top or the bottom. So for the top, we have x plus 2. That x plus 2 has a degree of 1. Now let's look on the bottom. We have a degree x minus 4, and that degree is also 1. So I would label this as a same, and then my equation would come from the leading coefficients. So in front of these x's is a 1 and a 1. So the ratio of leading coefficients would be y equals 1 over 1, and that's my horizontal asymptote. HA, y equals 1 over 1. I know 1 over 1 is just 1, so I could also just put 1. That's how that'll work. We will do some more examples of this. But now we have our last option for horizontal asymptotes. Horizontal asymptotes can also have the degree of the denominator be smaller, smaller than the top. The degree of the numerator is bigger than top. I call this the big top case. That's my nickname for this. When that happens, there is no horizontal asymptote. So in terms of easiness, this might be the best one. When you have a big degree on top, there is no horizontal asymptote. All we have to write is none. So let's practice this process. We're going to start with horizontal asymptotes, and I'm going to do all 5, 6, 7, 8, and 9 on this next page. And then I'll come back and do the vertical asymptotes for all of them. Since we just talked about horizontal asymptotes, I want to do those first. So for number 5, we have f of x equals 3 over x plus 1. The degree on top, well, I don't see any x's, so that's just 0. The degree on the bottom, there's only an x with an exponent of 1, so that's a 1. Well, that's a big bottom. So my horizontal asymptote, whenever I have a big bottom, is y equals 0. And that's it. We just found the horizontal asymptote from the equation. Looking over at number 6, we have a degree on top of 1 again. And then on the bottom, we have another degree of 1. Those numbers match, so this is what I called same. So now what we need to do is we need to take the ratio of leading coefficients. So y equals LC over LC. I'll make that little note right there. So looking back at my equation, my leading coefficient in front of x is 1 on top, and then my leading coefficient on the bottom is also 1. So really my horizontal asymptote is just y equals 1. And there you go. Number 7, my horizontal asymptote comes from a degree of 0 on the top and a degree of 1 on the bottom. Well, that's a big bottom. Every time you have a big bottom, the horizontal asymptote is y equals 0. On to number 8, f of x equals negative 3x plus 5 over x plus 2. We have a degree of 1 on the top because that x has an exponent of 1. And on the bottom, we have a degree of 1 as well. So this is going to be just like number 6. My degrees are the same, so I need a ratio of leading coefficients. Y equals LC over LC. So let's take our leading coefficients off of this. In front of x on top, we have a negative 3 this time. So I'm going to put negative 3 on top. And on the bottom, once again, we just have an x, so that is just 1. So my actual horizontal asymptote is just y equals negative 3. So that one was a little bit more complicated, but not all that bad. So just take the numbers from in front of your x's. Whatever is the highest degree, that's the leading coefficient is in front of that. All right, on to the last one, number 9. We have a degree of 3 on top and then a degree of 2 on the bottom. Well, that's a big top, and whenever the top is the biggest, there's no horizontal asymptote. So we just write none. Awesome. Horizontal asymptotes, not all that bad. Vertical asymptotes, in my opinion, are even easier. It's just a simple equation that you just have to know where to look. So for vertical asymptotes, we're looking for undefined elements in the bottom. So what ruins our domain? So take the denominator, for number 5, x plus 1 is our denominator, set it equal to 0. Solve this, you get x equals -1, and that's in fact your vertical asymptote. So your graph will not want to cross x equals -1, a vertical line where x equals -1. Over to number 6, just take the denominator yet again, x minus 2, set it equal to 0 because we do not want 0 in the bottom. Solve this and you get that the vertical asymptote is x equals 2. Because vertical asymptotes always follow the same pattern, I think that these are a little bit easier than horizontal asymptotes, especially if you can handle the domain that we did on the front side of the sheet. Looking at number 7, we have x minus 5. Set that equal to 0, and that tells us that our vertical asymptote is x equals 5. Pretty straightforward. Looking now at number 8, we take x plus 2, our denominator, set it equal to 0, and that tells us when we solve that our vertical asymptote is x equals -2. So these are all the vertical lines, dotted lines that we'd put onto our graph to indicate where our rational changes direction and breaks into two different pieces. Over to our last one, we have a little bit more complicated. X squared minus 1 is in our denominator. So I'll pull it out and set it equal to 0. But if you have to solve this like an equation, it's not just adding 1 over, because you still have x squared. If you add 1 over, you get x squared equals 1, and x squared is not the same as just an x by itself, so we always need x by itself. So how do we get rid of a square? We square root. But the important part is, whenever you square root, you always have to put a plus or minus in front of it. So x equals plus or minus the square root of 1. The square root of 1 is 1, so x equals positive and -1. So our vertical asymptotes, we have 2 this time, are both -1 and +1. So it's possible to have multiple vertical asymptotes. It'll cut your graph up several times. So in this case, you can see it's at -1 and 1 because we solved that equation. You could also factor number 9 like we like to do at the beginning of all work with rationals. Factoring would give us the same exact answer. As I mentioned before, though, vertical asymptotes were not the only thing that created undefined elements in our domain. This next word, holes, is the other thing that will create undefined elements in our domain. So sometimes a vertical asymptote will be the part that we cut out of our domain, but other times it will have a hole. Our rational function will have a hole. So what does that mean? Just visually, if we had a graph, I'll draw a quick little graph right here. A graph of a rational function, let's just pretend it has a vertical asymptote right here, and it has a horizontal asymptote right here. And our graph had 2 pieces. The left side was over here, but the right side, its second piece, has a circle missing out of it. That circle right there is our hole. It's a piece of our graph that we just jump over. It's just one little spot that's missing in our graph. So it's not as big of a hole as I drew on this graph. You wouldn't even see it if we typed it into Desmos. You'd have to know that it was there. But a hole is basically just skipping over. So your graph continues on pretty nicely, but then there's one value missing out of it. So if we're going to define a hole, it occurs when factors cancel. They're also called removable. So vertical asymptotes were non-removable. Holes are removable discontinuities. The reason for that is we removed them. We canceled them out. So that's where that name comes from. You find holes before naming the asymptotes. So I know we learned asymptotes first, but holes is something you would check for before you actually get to asymptotes. So to find the coordinates of the hole, the x value will be the 0 of the canceled factor. So just like we took the vertical asymptote and set it equal to 0, or the factor for the vertical asymptote set it equal to 0, we'll do that for holes. but it's only from the canceled factor. And then we also have to find the y value. So we need both an x and a y value for a whole. And to find y values, you just plug in x values. So let's see this in action with 10, 11, and 12. It's asking us to give the coordinates for the whole in each rational graph, then to give the equations of the vertical and horizontal asymptotes. So we'll get to the wholes, and then we'll do the vertical and horizontal asymptotes. F of x equals x plus 2 over x squared minus 4 for number 10. Well, I see a difference of squares in the bottom, x squared minus 4. So I'm just going to go ahead and factor this. X plus 2 on top doesn't change. The bottom becomes x minus 2 times x plus 2. And now you might see, like we always want to do with our rationals, is we have stuff we can cancel. X plus 2 and x plus 2 cancel, which means our rational function can be rewritten as 1 over x minus 2. So that equation is helpful, but if we're looking for a whole, what we want to do is we want to take that canceled factor and set it equal to 0. So take x plus 2 from the denominator, set it equal to 0, and the x value in our whole is going to be negative 2 if you solve that equation. Subtract 2 from both sides, and you get x equals negative 2. But that's not the end. We now need to take negative 2 and plug it into this equation. So f of negative 2, plug in negative 2 everywhere you see an x, and you'll find the y value. Negative 2 minus 2 in the bottom. And we get f of negative 2 is 1 over negative 4. So our whole is at negative 2 comma negative 1/4. So that is how you would actually define a whole. You factor and cancel, and then when you cancel, you take the canceled factor from the bottom, solve it just like a vertical asymptote, and whatever x value you get goes right back in to the function you created after you canceled. So let's do that again for number 11. So number 11, we have f of x equals x squared plus 5x plus 6 over x plus 2 times x plus 4. So the bottom is already factored for us, so that's nice. So I'm just going to factor the top right above this, just to save myself some space. I need an x puzzle that multiplies to 6 and adds to 5. That's going to be 3 and 2. So we have x plus 3 and x plus 2. So now I'll just scratch this out since we factored it. We have x plus 3 and x plus 2 on the top, and x plus 2 and x plus 4 on the bottom. Those x plus 2's will cancel. So if we are asked to find a whole, let's take only the canceled factor, x plus 2, and set it equal to 0. So we got x equals negative 2 is part of our whole, but not everything. We need the y value. So if we need the y value, we need to simplify this rational up top. Since we canceled the x plus 2, we're going to take x plus 3, leave it in the top, and x plus 4, leave it in the bottom. Now we need to find the y value by plugging in our negative 2. So f of negative 2 is negative 2 plus 3 over negative 2 plus 4. So our y value is actually going to be 1/2. So our whole is negative 2 comma 1/2. Once again, we factored and canceled, and the thing we canceled produced a whole. And then we took that x value and found the y value to know exactly where that whole was. Think back to the picture up top. We have to know precisely where this whole is on this graph. If we don't know, then we might just be skipping over an x value, but we also need to skip over the y value. So we have to be precise with it. Last example of finding a whole here for number 12, we have x times x plus 8 over x cubed minus 4x. The top is nice and factored for us, but the bottom also has a GCF, and then will become a difference of squares. So x times x plus 8 on top doesn't change. The bottom becomes x times x squared minus 4. Let's just think about x squared minus 4. We can factor that, and it'll become x minus 2, x plus 2. but that's not going to cancel with x plus 8. So I'm not even going to bother with that for now. So all I'm going to cancel is those x's out front. So if I'm working with a whole, I take the canceled piece, set it equal to 0, and then we're good. X equals 0 is part of our whole. So start it with 0, and now we just need to find the y value. But the y value always gets plugged into what's left. So we need f of 0, and we're going to plug 0 into x plus 8, so 0 plus 8. And then on the bottom, x squared minus 4, so 0 squared minus 4. So when we plug that 0 in, we're going to get 0 over negative 4, which is just negative 2. So our whole for this rational happens at 0, negative 2. So once again, a couple things to keep in mind. You're canceling, making a removable discontinuity called a whole. And when you cancel, you're finding the x value by setting that factor equal to 0 that you canceled. Then you use that x value, plug it into the new equation from what you get when you cancel, and that will give you the y value. The entire piece is the whole. So you have to have a coordinate to find the actual whole. If you don't have the coordinates, you haven't actually found the whole yet. So all of these boxes would be your actual answer for 10, 11, and 12. So those problems asked for vertical and horizontal asymptotes, you're welcome to practice those. I'm just going to move on to intercepts now. And hopefully this is familiar territory. So we learned a couple new things: vertical asymptotes, horizontal asymptotes, and wholes. And those are all special for rational functions. They might show up in some other functions later, but they're relatively new to us. Here, intercepts is familiar. So let's get back to the basics. X-intercepts, that's where a function crosses the x-axis. That's nice and familiar. We can also call them solutions, zeros, or roots. For rationals, they're found by setting the equation equal to 0. That's pretty familiar. The shortcut is just set the numerator equal to 0. X-intercepts don't have to be that complicated. If you're given a graph, just look at where it's touching the x-axis. If it's not touching the x-axis, there are none. Y-intercepts we're also familiar with. It's where the function crosses the y-axis. And these are a little bit more difficult, but not all that bad. They're just found by plugging in 0 for any x in your rational. Some rational function graphs will not have x or y intercepts because of the asymptotes. So be careful with that. If your asymptote is at the x or y axis, meaning y equals 0 is your horizontal asymptote, or x equals 0 is your vertical asymptote, be careful. Those are not x or y intercepts anymore. So let's do some actual problems now. On the back page of this, we have 13, 14, 15, and 16, and these 4 problems are just asking us to find the x and y intercepts. So for x-intercepts, we are going to set the equation equal to 0, but the shortcut's just the numerator. Don't even worry about the bottom. So 0 equals x minus 4 is my numerator, and so x equals 4 is my x-intercept. Except, hold on, we don't just write x equals 4. We always write it as an ordered pair, 4, 0. X-intercepts always have 0 as the y value. Now the y-intercept portion, we set the entire equation equal, or apologies, we do not set the entire equation equal to 0. We plug in 0 anywhere we have an x. So y equals 0 minus 4 over 0 plus 1. I make mistakes too every now and then. So y equals 0 minus 4 over 0 plus 1. That just simplifies as negative 4 over 1. So y equals negative 4 is our y-intercept. But once again, we don't just write y equals negative 4. We put it as an ordered pair. So it's 0, negative 4 for our y-intercept. And that's it. Let's move on to number 14 now. We have x plus 2 over x minus 5. And if we want the x-intercept, we take the top as a shortcut and set it equal to 0. So x equals negative 2 is what would come out of that. but we don't write it as x equals negative 2. We write it as negative 2 comma 0. For the y-intercept, change it to y equals, and then any x, change it into 0. So 0 plus 2, 0 minus 5. This would simplify down as negative 2/5. So y equals negative 2/5, but we write it as 0 comma negative 2/5 for our y-intercept. The reason that those zeros exist in the same places is, think about it. The x-intercept is where you're touching the x-axis. Well, along the x-axis, every x value is 0. Or y value, I apologize. Every y value is 0. So that's why this 0 right here will never change for your x-intercept. It's always going to be 0 in the second spot, in the y value spot. On the y-intercept, you're touching the y-axis, and every x value on the y-axis is 0, so these zeros also will not change. So, just something to note as to why that always occurs like that. 15, we have f of x equals 2 over x plus 5, and we're going to start with the x-intercept, so we take the top, and we set it equal to 0. But hold on, think about that. Is 2 actually equal to 0? No. So if you get a false statement, your answer is that you do not have an x-intercept. Anytime there's a false statement in math, alarm bells should be going off and you should think, uh-oh, something's wrong. I probably don't actually have what's happening here. So alarm bell went off. We do not have an x-intercept because the top is not indeed equal to 0. For the bottom, the y-intercept part, we are going to set y equal to 2 over 0 plus 5 because we take our equation and plug 0 into all the x's. Well, this just simplifies to 2/5, so our y-intercept is just 0 comma 2/5. So we do have a y-intercept. It's possible to have a y-intercept but not an x-intercept, and vice versa. And it is also possible to have neither. But in this case, we just had a y-intercept. All right, last one of these, number 16, we have x plus 1 over x. Let's do our shortcut. Numerator set equal to 0 tells us that x equals negative 1 is part of our x-intercept, but we write it as negative 1, 0. For the y-intercept, every x gets a 0, so we have 0 plus 1 over 0. Now think about that. If we simplify this, we get 1 over 0. What are we doing with that 0? We're dividing by it. Well, we're not allowed to divide by 0, so this does not exist, meaning we don't have a y-intercept. It doesn't exist because x equals 0, if we think about our domain, is not a part of it. Our domain is all real numbers, but x does not equal 0 because domain comes from setting the denominator equal to 0, and anything that comes out of that is a restriction, something we pull out. So we can't plug in 0 for x, so there is no y-intercept. So on to the last feature that we're going to talk about in these notes for rational functions. It's another familiar topic. It's end behavior. For end behavior, there's a special trick for rationals. So end behavior is what happens at the left and right ends of your graph. But for irrational functions, they're usually leveling off, not going up or down. So the leveling off is what we saw earlier. It's our horizontal asymptote. So all you have to look for is a horizontal asymptote. So if you have a horizontal asymptote, you have the answer to your end behavior. So you can use a graph, you can use an equation, either one will work. So if you see a horizontal asymptote on a graph, that's the same as your end behavior. We'll write that. I'll show you how to write that in a second. If you find it from looking at an equation, it's the same thing. So for 14, 15, and 16 here, which I know that the numbers have repeated themselves, this should actually be 17, 18, 19, but we can get over that. We have f of x equals x plus 3 over x minus 4, and we want to start with, do we have a horizontal asymptote, and then jump to end behavior. So horizontal asymptote, we always check the degree. The degree on the top is 1, the degree on the bottom is 1, so we have what I call same. So we always need y equals LC over LC. LC stands for leading coefficient. and the leading coefficients are both 1, so our horizontal asymptote is 1. So we do indeed have a horizontal asymptote, so this is how we address the end behavior. The left side of our graph will flatten out and get really close to 1, so we say it approaches 1. And the right side of our graph will get really flat and approach 1, so we say f of x approaches 1. So as x approaches negative infinity, the left, f of x approaches 1. And as x approaches positive infinity, the right, f of x approaches 1. Next one, we have f of x equals 5 over x minus 1. If we check our degree, there is not a degree on top, 0. And on the bottom, we have a 1. This is a big bottom. Anytime you have a big bottom for your horizontal asymptote, you have 0. So y equals 0. So same thing for end behavior. As we go to the left, your graph will flatten out along 0. As we go to the right, your graph will flatten out along 0. Now to the last one, we have 2x plus 5 over 4x minus 1. The degrees are going to match again. We have a 1 on top and we have a 1 on the bottom. So we are going to need the ratio of leading coefficients, that LC over LC. So let's take those leading coefficients. I see a 2 on top and a 4 on the bottom. So y equals 2 over 4, but really y equals 1/2. We don't write 2/4, we simplify to 1/2. So our horizontal asymptote is y equals 1/2. Just like the other two, our end behavior will match exactly. Our graph will approach 1/2 on the left side and 1/2 on the right side. That's it for end behavior. It's pretty straightforward for rational functions. So we just learned a bunch of different features for rational functions, asymptotes, holes. You know x-intercepts, but we know how to do them, x and y-intercepts, but you know how to do them now for rationals. And then this special case of end behavior is just the same as our horizontal asymptote. So now you can tell a lot of different things about rational functions.